Hello, everybody. Thank you for having me. My name is Jeniveve Pearson. I'm a finishing year graduate student at the University of Arizona working with David Sand. And today I'm going to talk to you about the long-term multi-wavelength observations we've gotten of supernova 2017 EAW and what that can tell us about this system. So this beautiful background picture right here is a J2ST image. And the first thing I think of when I see this is, wow, that's a lot of dust. And dust in today's universe is primarily made by AGB stars with some contribution from the winds of massive stars. But the early universe is also dusty, and that's somewhat unexpected, given the fact that intermediate mass stars won't yet have reached their AGB phase for these higher mass objects. So what is causing the dust in the early universe? It could be core collapse supernova, much like the one you see right here in the center of this image. So if core collapse supernova are producing the dust in the early universe, that means they need to be making between 0.1 and 1 solar masses of dust each supernova. So every single supernova just means making this much dust. And as you can see from this plot, very few supernova we've observed have this much dust in them. And almost all of them that we've observed, or in fact, all of them that we've observed that have this much dust were decades post-explosion. But we have a lot of observations of supernova at early times that just aren't completely missing this theoretical expectation. So what's happening? Are we maybe missing this dust? Maybe it's optically thick in the ejecta, or it could be that supernova slowly create dust over time. So in order to try and solve this problem of how supernova create dust, we need to look at this crucial early time when the supernova are the dust in the supernova is potentially still warm enough to see in the mid-infrared, and also the supernova are young enough that they're still emitting and we can still observe them. So to that end, we had a cycle 2 J2ST program to observe 9 normal core collapse supernova that were less than 7 years old and older than 2 years old, using the full mirroring filter set. So really trying to understand the mid-infrared evolution of these objects. The oldest supernova in this sample is supernova 2017 EAW, which is located in NGC 6946. And because of its close distance, we have an extensive optical and infrared data set, including the detection of carbon monoxide at roughly a year post-explosion. I think Sam Rose will talk about this a little bit in the next talk, but that basically just means that at that point, the ejecta was cool enough to begin forming dust. So we should expect dust formation in this supernova. And excitingly, in addition to just our J2ST images in cycle 2, it was also observed in cycle 1 as part of a separate program. So we have multi-epoch J2ST information, and we can see how the mid-infrared is evolving with time, really understand how that dust is evolving over a year. So if this dust is newly formed, we expect to see that dust cool. So the SED should move redward as the dust condenses and cools. And maybe also we should expect to see the mass of dust in the system increase with time. Perhaps both of these things at the same time. And that's not what we see at all. So this is the cycle 1 observations are the pink diamonds, and the cycle 2 are the purple circles. And you can see that the SED has dropped from one cycle to the next. Now, there's only a year between these observations, so not a huge time difference, but certainly we're not seeing the evolution that we would expect. And so when we model this dust, we try a bunch of different geometries and a few different compositions, and we find that this dust is best fit with 2 silicate component dust, so a hot component and a cooler component. And regardless of what geometry we choose, we find that the dust has a mass of about 5 times 10 to the minus 4 solar masses. And that's both cycles have of that dust mass. There's not a huge drop in the luminosity. And the majority of the dust is in this mid-infrared region right here. And that's cool dust at about 157 Kelvin. And that's, again, the same in both cycles. You can see the peaks of this SCD don't change over time, which is a strong indication that that temperature is the same. Furthermore, we can't well constrain the radius. That's one of the ways we could be able to tell if the dust is newly formed or pre-existing, is whether it's inside or outside the ejecta. But this dust is consistent with being optically thin. So we can't use this as like a really strong smoking gun of like, okay, this is newly formed versus pre-existing. So that leads us to looking in the optical. So this is where Keck comes in. As part of, we got some NASA Keck time to observe all 9 of our supernova in the sample with Keck LRES, and got this beautiful spectra, the most exciting of which, in my opinion, is of 17 EAW right here. You can see that beautiful H alpha in the middle. That big, broad, boxy H alpha is like a hallmark of CSM ejecta interaction in these supernova. And excitingly, it hasn't really changed much in almost 2,000 days. So here, the blue spectra is the spectra at 900 days post-explosion of this object. And then here we have it at almost 2,700 days post-explosion. And you can see that the profile of that H alpha is very similar, which indicates that it is at a similar level of CSM interaction as it was almost 2,000 days ago, which is very exciting. And we do actually see evidence of this elsewhere as well. This supernova is still UV bright, even though it's 7 years post-explosion at the time of the HST observations. And we have multiple HST observations in the infrared. So we can actually map the UV as well and try to understand how it's evolving over time. And so when we look at the decline in the UV, and we compare that to the decline in the infrared, we find that they are pretty similar. And so here you can see that blue point is the UV, and these cluster of mid-IR points are probably the most well-constrained of the mid-infrared points in the JRC, and they're very similar changes. And now if the UV and the IR are declining similarly, then that would suggest that perhaps they're probing similar material. The UV is coming from the interaction of the CSM and the ejecta, and the IR is coming from the dust emission. So if they're probing the same material, then that would suggest that the dust is co-located in the CSM, which would potentially suggest pre-existing. And when we combine that with the fact that we have evidence for CSM interaction, continued CSM interaction in the optical with that UV bright, and then also that super nice boxy H alpha profile, and the fact that we're not seeing the dust evolution in the SED that we would expect. This is real strong evidence altogether that dust in the mid-infrared, at least, that we're seeing is pre-existing. Now, don't worry, that doesn't mean that there's not newly formed dust in this system. One of the ways that we can look for newly formed dust in the case where that dust is optically thick, and we would not be able to see it in the mid-infrared yet, is to look at the optical spectra. And you can see here, especially in the oxygen profiles, there's like a bite taken out of this profile, which suggests that it could be dust attenuated. So the dust in the ejecta is blocking some of the light from the far side of the ejecta as it passes in our line of sight. And so really one of the only ways we can be able to see and try and understand this dust at early times could be through the optical spectra, if this is what is happening. All right. So altogether, what does that mean? The multi-wavelength evolution of 17 AW suggests that at least the stuff that we're seeing in the infrared, that dust, is primarily pre-existing. And that means that that dust was formed in the CSM before the star exploded. Why is this, so we set out to try and solve the problem, how does dust form in supernova? And instead, what we're really probing is how does the progenitor of these objects die? So red supergiants have what we think is a period of extended mass loss at the end of their lives. And we really don't understand this period. It lasts maybe 1,000 years. It's very difficult to observe directly. And so we're using supernova as an indirect code. And dust, if this dust is in the pre-existing, this dust could give us the opportunity to look at when is the onset of CSM, that higher mass CSM around these objects, and really try and understand how this is happening and how these red supergiants die. And to that end, what about the rest of this sample? So this is preliminary work by postdoc in my group, by Brian, and we have just a few of the SEDs. The pink circles here in the background are 17EAW. You can barely see them because all of the SEDs look uncannily similar. So this is the mid-infrared data. And so perhaps this means that all of these are pre-existing dust, and that this is something that we'd expect to find with most red supergiants that are dying. However, when we look in the optical, they look vastly different. You can see here, this blue spectra is that 900-day 17EAW spectra. It's roughly between the two epochs of these two supernovae that you're comparing to. And so this is telling us something about the CSM itself. What is going on with the CSM? Can we understand the components of the CSM? Also understand a little bit about the structure of the supernova itself. And then try and understand, how much dust is in these things based off of the line profiles. And so finally, with regards to supernova dust science in general, I think it's really important that we try and untangle the pre-existing from the newly formed dust. And that requires both UV and infrared observations from space. But crucially, it is important that we do ground-based follow-up and get optical spectra as late as possible. And one of the only observatories that can do that is Keck. So it is going to have a huge role in the future of supernova dust science. So I'll encourage you to check out the paper on 17EAW. And with that, I'll take any questions.